but random walks. Ramanujan complexes, but plus minus.
Quite so. Thank you, Ori, for the invitation. I'm very happy to be here. I'm always here. So this talk is about random walk on Ramanujan complexes. The assumption is that nobody knows what it is, and we don't need to. We won't go very deeply into this thing, but the idea is that we learn some. I hope we learn something which are also relevant to other areas. So everything starts with expansion on graphs. So let's say we have a k-regular graph. And I'm interested in the expansion, which means that I take a set, I do the adjacency operator, and I want to say how much my set expands. And a lot of time this is stated, and I want to relate it to the spectral theory of the graph, and this is usually stated in terms of the Chigger inequality, but I like another way that I found to think about it, which is the following. So let's say I have a set S, and then I'm looking at what happened when I take the adjacency operator, and I want to ask if it became bigger or not. So, and my graph is k-regular, and so there are two extreme things that can happen. One of them is that every vertex in S has k different neighbors, so no two of them share a neighbor. And the other thing is that for some reason, all of them have the same neighbors. So I get to the same vertices from all my vertices. And what happened in this case, so this is like the best expansion. And this is the worst expansion. And what happened with the spectral theory is exactly the opposite. So if I start here, I take the adjacency matrix, apply it to the characteristic function of the set, and I'm asking how much it blew up. So in this case, I just get the characteristic matrix of the characteristic function of the new set, right? Because everyone is there once, and this thing is the square root of the size, which is square root of k s, because it blew up. And this is square root of k times the original function. So I got the spectral behavior of square root of k. And on the other side, here, what happened is that I apply this. What I get is k times the characteristic function of as, because everyone got k from k different vertices. So now I get k times the square root of as, and now the size of as is just the size of s, because my set stayed the same. So I get k times. Well, let's do already. So
is your graph directed or not?
yeah, I'm thinking about directed graphs, but you can think about undirected.
Yeah, of course.
Yes.
Are they mostly infinite or finite?
Both of them are interesting to us. But I'm just trying to say now that this is something which the first time I saw it confused me. If my matrix blows up characteristic functions, it's actually bad expansion. So k is bad, and square root of k is best in terms of expansion. That's how I want to think about it. So we're trying to find graphs with adjacency spectrum small. And that's expanders. Small adjacency spectrum. So now there is a theorem of Alon-Bopana. If Gn is a family of undirected k regular graphs, and the number of vertices goes to infinity, then let's call the okay, I didn't say what then the second eigenvalue of the adjacency operators eventually cannot drop below 2 square root of k minus 1. So this would be lim sup, and this is as n goes to infinity. What? Okay. I had 50%, so I went for it. But this means that if I'm trying to, let me say the way I understand it, if I'm trying to build an infinite family of k-regular graphs where the second eigenvalue is all the time beneath 2 square root of k minus 1, I will fail. Or beneath this minus epsilon, actually. I will fail. There is no such family. Why second eigenvalue? Because for a finite graph, the first eigenvalue, I cannot do anything about it. It comes from the constant function, and it's k. So there is this k coming from the constant function, so I'm interested in all the others. So this tells us also that we cannot get all the way down to square root of k, at least when the number of vertices go to infinity. We are bounded by roughly twice this thing. And what happened is that this is a feature of undirected graphs. So what we will see soon is that when you go to directed graphs, you can go all the way down to square root of k. And this was used in a fairly recent work of Yuval Perez and Eyal Lubetsky to understand random walk on Ramanujan graphs. So let me say what is Ramanujan graph. G is Ramanujan. Ramanujan graph. If the second, let's say if the second eigenvalue is bounded by this thing. And let me explain where it comes from, because it's also important. This is, okay, no, let's give the full. If every non-trivial eigenvalue is in the strip minus 2 square root of k minus 1, 2 square root of k minus 1, where non-trivial means not the first eigenvalue, so not k, that's a trivial, and so this is not plus or minus k, because minus k is also kind of trivial. It tells you that the graph is bipartite, and you know exactly where the minus k comes from. It comes from partitioning your vertices and putting 1 here and minus 1 here, and you get minus k. So you want everything else which you don't understand to be in this interval, and this interval is the spectrum of the k-regular tree. So this is a k-regular tree, and I should say the L2 spectrum. So this is a spectrum of adjacency on L2 function of the k-regular tree. This is due to Kesten. So there is something which is qualitative about Ramanujan graphs. It's not only the thing which gives you this quantitative bound for the eigenvalues, it's also the graph which spectrally behave like a tree. And except for these eigenvalues. So no finite graph is really a tree, but the point is that you push everything which is come from finiteness to these eigenvalues, and everything else looks like a tree. And I was going to say something. Okay, so the philosophy, yes, and the tree is the ultimate expander. That's what I wanted to say, because you take a set on the tree and it will expand. It will expand and expand and expand. That's the tree. That's what I wanted to say. So in a sense, you expect these to be the best expanders, and it's been an ongoing quest for the last 30 years to understand in what sense. And we still have new results like the work of Lubetsky and Perez. So.
Ori, you say everything looks like only a tree. Does it apply not just to the bounds of the spectrum, but to the spectral matter as well?
You're right. It's not also on the tree. You don't have this. This would be the best thing, the square root of k. But also on the tree, you get this because you can't really all the time go farther away because you also go back to where you came from, and this eventually causes this twice thing. And it will all disappear when we move to directed graphs. So here is Lubetsky-Perez. What they show is that when you move to non-backtracking random walk on a Ramanujan graph, has a, let's say, optimal cutoff. So I'm going to put here k plus 1 regular, and I want this to be k plus 1 regular because this makes the non-backtracking random walk k regular. So this thing is now a k regular operator. Now, I think about it like that. If I have a G, which is a Ramanujan or any k-regular graph, I make from it a digraph, which is a k minus 1 regular, and which encodes the non-backtracking random walk on G. So this is the k minus 1 regular digraph encoding non-backtracking random walk on G. What does it mean? The vertices of this digraph are the directed edges of G, and two directed edges are directed neighbors. Now we have a digraph. So this is x, y, and z, w if y equals z. So this is actually a path. And w is not x. So this is a path, but it's not a backtracking path. It's not going and then coming back. So this walking on this directed graph is exactly like doing non-backtracking random walk on the original graph. And the point is you understand non-backtracking random walk on the original graph by studying this digraph. And nobody likes digraphs. For a good reason, because they're not symmetric, and then things are hard. But I think the point of the paper here is that you want to do that. That you have to, I think about this paper as like putting the digraph and analysis of non-symmetric matrices in a spotlight, that you want to understand them, even if you only care about directed, undirected graphs. So here is a first point. So the non-trivial spectrum, okay, let's do it like that. If G is Ramanujan, then the non-trivial spectrum of the directed graph, which encodes the non-backtracking random walk on G, is bounded by square root of k. So this is G is k plus 1 regular Ramanujan, and this thing is k regular because we lost one edge because of the backtracking thing. So we have a k-regular graph with spectrum bounded by square root of k, which I started by showing you that this looks like the best you can hope for. Sorry? Finite. This is a finite graph. Yeah. Complex. Yes. Sorry, I heard compact and it didn't make sense. Complex, yes. This is the non-trivial spectrum, which is now in C. You're right. So it's contained in the disk of radius k. So square root of k. And we have k here. So this is all. This is due to Ihara, Hashimoto. I think in a sense this follows from work of Ihara in the 60s, but Hashimoto was the first to translate this to the non-backtracking random walk. And so this is very old, but and it looks great if you're interested in expansion, but the point is this is not very helpful as it is. Why? Well, the point is that for non-symmetric matrices, the spectrum doesn't tell you a lot. What tells you more is the singular values. And this doesn't tell you anything about the singular values of the matrix. And the question is what to do. And this is what Eyal and Yuval understood. And so this is Lubetsky. Perez. By the way, this is if and only if. Even. And this is a classic fact that is understood for many years. But what Lubetsky and Perez understood is the following. The adjacency matrix of this directed graph is unitarily equivalent. So you know that if a matrix is symmetric, then it's unitarily equivalent to a diagonal matrix with the eigenvalues on the diagonal. What they understood is that it's unitarily equivalent to the following matrix. So you have here K coming from the constant vector, and then you have a lot of blocks of size 2 by 2. And so these are 2 by 2, and then at the end you have again blocks of size 1, which have eigenvalues plus and minus 1. So these are plus and minus 1, which are very small. You don't care about them. K is the constant, the trivial eigenfunction, the trivial eigenvalue. And here is what the important part. Here's where thing happening. Every block like this looks like square root of k, and here k minus 1. And this is in terms of magnitude. So actually this is a square root k times some theta, which is in the unit circle. So it's a value of magnitude, square root of k. But we don't care about this magnitude, about this phase. About the phase, the magnitude is what's important for the analysis. And you want to understand this. By the way, I think that the problem with how I would go to this question is that, okay, the non-backtracking random walk is still, it's not symmetric, but I can still understand this. It's still diagonalizable. So I think that the natural thing is to diagonalize it and then start working from there. And that's very hard. So what they do instead is not diagonalize it, stay with a non-diagonal matrix, but still keeping an orthonormal basis. That's the important thing here. This is still an orthonormal basis, which allows us to do analysis. Now, if you check this matrix, let's call this block B for block. So we have a lot of blocks of size B, and then this trivial one. As we see, this is 0. The spectrum is square root of k, which is good. But we say we care about the singular values or about the matrix norm, which is the maximal singular value. And if you compute the matrix norm, which is the maximal singular value of B, what you get is k, which is as bad as can be. It's like having, again, the trivial eigenvalues. It's like having a disconnected graph, right? When k repeats in a directed graph, it means your graph is disconnected. Here you get k and k and k again and again and again. So it looks very bad, this decomposition, when you look at its spectral decomposition. But the point is, when you do analysis of random walk, what you care is about powers of your matrix. What you really want to do is, if you were looking at random walk starting from some v0, at time t, what you see is 1 over k to the t, a to the t, 1 v naught. So what you really care about is powers of your matrix, and the spectral norm of a power of this matrix. So let's really do it. It's 1 over k. So I move to the basis where I see this thing. But now I'm raising it to t. So what I get is 1 over. So let's do take also the square root of k out. So I get 1 over square root of k to the t. And here I have 1. And this is something like square root of k, 1 to the t. So let's do roughly, because I forgot this minus 1, just to make things nice. And this thing we know how to take to the t power. This is 1 over k to the t, 1 t, square root of k, 1 and norm.
Square root, the over 2 of square root.
What?
It's the square root.
Here. Thank you. You're right. And and the norm of this thing, you have to compute it because it's not the spectrum. It's a singular value, but it's more or less this is the singular value of this matrix. So what you get is a t over square root of k to the t minus 1. I like it that you can do the entire computation by hand. And the point is, if your matrix was normal, symmetric or normal, then we would have this to the t, a to the t, would be bounded by 1 over square root of k to the t for a normal. So the point is, what you lost is instead of square root of k to the t, you got square root to the k t minus 1, and you got this t. You paid in this t for the non-normality of your matrix. And how much time do I have? Half an hour. I'm wondering whether I should show you why this gives you the result of Lubetzky and Perez. So, what? Yes? Okay. So, this is very annoying. So, the idea is that, let's say ST V is the t-sphere around a vertex. So this vertex is a vertex in this directed graph. And and the claim is that the sphere of radius log kn plus, I think, 3 times log k log n v covers almost all vertices, or contains. And this is the remarkable behavior that they expose here. Because you have a k-regular graph. So if you're doing log kn steps, n is the number of vertices. if you're doing log kn steps, that's the minimum you need to do to try to cover almost everything. And they show that once you do this plus the log-log addition, you really get almost everything. So it's like this miracle. And the proof is, so I wrote it down because I thought you might want me to explain it. So let me just write what I wrote here. So I'm looking at the vertices I didn't cover over n squared, and I'm saying this is like going over all the vertices which I didn't cover after t, that I didn't get to after t step, 1 over n squared. So this is really the same thing, but this is the norm of the random walk starting from p. I have a mistake here, I think. No, that's okay. I just want to say that this is smaller or equal to this square. No, that's okay. This vector, so this is the probability vector, minus 1 over n, restricted to the vertices which I didn't visit. So v minus st. So this is exactly the same, because all the vertices that I didn't visit in t steps get 0 here. So this 1 over n gives you this 1 over n squared. And this is exactly taking, this is equality. And then I can say, okay, this is smaller or equal to the same thing without the restriction. So going over all of v. And this is the norm of 1 over k a to the t, 1 over 1v square. Did I get it right? So the point is that this 1v decomposes to the constant function and the component in the orthogonal complement.
Didn't we use some projection here?
What?
Didn't we use some projection here?
Going from here to here, no?
Minus 1 over n to
This is the projection of every probability vector on the constant. I think this is what you mean. This is why, and the constant function, this is the stationary distribution. It stays fixed under this Markov operator, and everything else decays like this. That's the point. So what we got here is...
What is the 1 over n disappeared?
yeah, exactly.
In the last equality.
You need to write something like
Previously we had
a restricted to some
This, yes. Sorry. Yeah, 1v minus 1 over n. You're right. You're right. And the point is now I want to do the spectral analysis. I know a bound for this matrix. This I just bounded by 1. So this norm is bounded by 1, and this is what we bounded here. So we got t squared k to the t, minus 2. No, minus 1. And that's it. No, the k, that's square, so the square root of k became k. Okay, this is just from what we did here. We get this bound, and that's what we want. So now you have to play with it. You see that now you plug t equal this. You put this in t, and the point is that this log kn kills this part, and this 3 times log killed this part. We took the 3 to get over this 2. And you're nodding, and I think you know that already. And so this is where this miraculous thing comes from. Okay, so this is the work of Lubetkin and Peirce, and they have very interesting consequences from this. I'm just showing a nice one fundamental thing which happens here. And then when Alex Lubotsky saw this paper or heard about this paper, he said, let's do the same for Ramanujan complexes. which is a higher dimensional analog of Ramanujan graphs. So Ramanujan graphs are a quotient of Tk with the same non-trivial spectrum. And then Ramanujan complexes would be the same thing. Well, quotient of, well, here we need to put something with some complex, infinite complex, with the same non-trivial spectrum. And what Alex put here when he started working on these things like 15 years ago is they define the building. So this is a Boatitz building. Boatitz building, which is, so the Boatitz building, or let's say of dimension D, is a D-dimensional contractible simplicial complex. So already from this, you see that when D equals 1, you have a one-dimensional contractible simplicial complex, so a contractible graph. And it's also regular, if you want. So a contractible infinite graph is a tree. I mean, every contractible graph is a tree. So this really generalizes trees to higher dimensions. No, I really want to work on complexes now. Why skeleton?
But you say it's a tree.
No, when D equal 1. When D equal 1, this is a tree. I just want to say that it's a generalization. You get this in particular when you take D equal 1. You get a Ramanujan graph. And, okay, well, it doesn't, I mean, you have to know this, you have to understand this, what it's building if you want to study this like you want to study the tree if you want to understand graphs. I won't go there. The point is that Alex wanted us to do the same for Ramanujan complexes. And the question is, what do we need? So what happened here was two things. One of them was why does non-backtracking random walk on Ramanujan graphs is so good in the sense of I get this remarkable behavior. We had two things. One of them is this unitarily equivalent to 2 by 2 block matrix. And the second was the square root of K spectrum. These are the two ingredients in Perez-Lubetsky. And well, what happened is for Ramanujan complexes, every adjacency operator on cells is unitarily equivalent to a block diagonal matrix. So here we have the degree of the matrix, the degree of the operator, and then we have blocks. And the size of the block for if we have a complex of dimension D would be what? D plus 1. That's a good guess because when we worked on a graph, we had blocks of 2 by 2, and the answer is D plus 1 factorial, which for 1 is the same. But yes. And it goes. But the point is, it really doesn't matter that it goes. It just need to be constant to do all these games with the spectral analysis. As long as these blocks are of constant size, we can continue. And this is, by the way, kind of a easy fact if you know your material. So these complexes come from groups whose representation theory tells you that all the irreducible representation have dimension bounded by this. And representation theory is used to break matrices into blocks. So you get the size of the blocks either for free.
What's the dimension of cells you are talking about here?
Of what?
What is the dimension of cells you are talking about?
Well, it's bounded by D, but I can take a walk on vertices, edges, triangles, anything.
But you have to fix a certain dimension.
Yeah, D. So I fixed the dimension D for the building. This is a building of dimension D.
But that's cells of much more dimensions that you are considering.
What? No, I'm thinking on the D-dimensional building, and I'm working on cells of dimension 0 up to D.
So you consider cells of all dimensions simultaneously?
Yeah.
Up to D.
Up to D. Well, there's nothing above it. Yes. And then, so this is the easy part. Also for graphs, I think Yuval and Eyal worked hard, and the proof is beautiful for this thing, but when Alex heard about it, he said, of course it decomposes to 2 by 2 matrices because this is a group. It has 2 by 2 irreducible representations. But the fact that you know something doesn't say that you know what to do with it. That's the thing. What?
The story actually, if you want to reflect, and in this room, Yuval Perez gave the talk, and he showed by elementary terms that you can decompose it to 2 by 2 matrices. And I saw that what he was doing is really the composition as representation of the Hecke algebra, that is associated with Hecke algebra. And with equal to, this is all representation of the Hecke algebra dimension 2, because D plus 1 factor, so Z factor 5.
Yeah.
And this is D plus 1.
Yes. So, but
If you have a good student collaborator, you go and tell him now.
so
This argument assumes LPS?
no.
For Ramanujan,
No.
No, I mean this Hecke algebra.
Alex says,
It's algebra argument is for every Ramanujan because
no. Your argument is for LPS. It works for prime P. Their argument works for any. Your argument works for a graph which is.
define Hecke algebra in the full automorphism group of the tree also.
Yeah, and then you're doing. Yeah, that's. So this is one thing, and it generalizes very easily. And the second thing is this. How do we make this thing? And so the first, we ask, why does the non-backtracking random walk on the tree, or on a Ramanujan graph, has this spectrum? And we started looking at operators on higher dimension. This is, by the way, work with Lubetzky. Lubotsky, and myself. So we started working on operators on the building. So the first thing we checked is that non-backtracking work on the building has spectrum bigger than square root of k. So we want to have the spectrum should be the square root of the degree of the operator. So k I always use for the degree of the operator, of my random walk operator. And I want the spectrum to be the square root of that in absolute value. So this doesn't work, but geodesic work does. So geodesic work tells you that you walk. So if I start, I'm working on edges. And so non-backtracking work tells me I'm going to a different edge, and I can't go back. So now I'm telling you, okay, you can go to this edge, that's okay, but you cannot go, for example, to this edge. So this is bad. Why it's bad? So the idea is that this is not a geodesic path because it's homotopic to this shorter path. I can squash this thing here. So this is why we call it geodesic. So geodesic walk on edges has spectrum bounded by square root of k, for example. So, and this is for us, this was a computation in representation theory. There is a group which makes an appearance here, which is GL3 over the p-adic, and the representation of this group were classified long ago, and each one of them contributes a block of size 6 by 6 here, and you compute the eigenvalues, and we computed the eigenvalues and checked that they're bounded by square root of k. So we got from this everything that Lubetsky and Peres got. And then we started looking at other operators, trying to understand when do we get this square root spectrum and when not. And luckily, we also found a paper due to Kang, which gives you many operators with spectrum bounded by square root of k for a Buatitz building of GL, DQP. Why luckily? Because at this point I said, okay, let's forget this project because it's not interesting anymore. We know that the representation are bounded in the size of the block are bounded from classical theory. He already showed that the spectrum is bounded by the square root of k. There's nothing for us to show left. But Alex and Deyal wanted to continue. And so we had to do something more. And eventually I was very surprised with what we did. I'm happy that they forced us to continue. Because up to this point, everything we did was taking an operator, computing the spectrum by representation theory. And it's quite hard. So eventually we found an argument which completely bypasses representation theory. And it understands why we have this phenomena. Where does it come from? So we say an operator A is collision-free if you start with a vertex or a cell or everything, whatever you walk on, and you take the adjacency operator, you see where you got to, and you never hit yourself. So you never run back to, you don't have something like that. It's collision-free if two walkers never meet once parted. And an example is non-backtracking random walk on the tree. So random walk, non-backtracking random walk is something which happens on edges. If two walkers on the same edge start walking, I mean, they can walk together, but after they part, each lives in a different subtree and they'll never meet each other. And what happened is that all the operators which had this nice property of spectrum square root were collision-free. And at some point I said, okay, I don't think it will happen if once we have a collision, it doesn't make sense that we have this optimal expansion. And Alex says, so let's prove that everything which is collision-free has this optimal spectrum. And I said, no way. And then we did that. So I was very surprising that this simple criterion is what you need. And the argument is also nice. So what we thought at first is that if P, or let's say if A is collision-free, then the spectrum of A is bounded by square root of the degree. So that was the idea. And we actually convinced ourselves that this is true and then wrote half of the paper before we realized that we didn't really prove it at any point. We just convinced ourselves. And then we said, okay, we have to prove it. We set for a long time to prove it, and it's false. So wrong. And here is a counterexample, which eventually we found. So this is my graph. I'm taking k equal 2. And what I'm doing is this guy, everyone goes like this. And also to the neighbor. And so on. Now, at the next step, this guy goes, everyone still goes down. But I cannot go here anymore because then I will have a collision. So now I start doing things like that. Okay, and at the next step it's like this. And so on. So this thing is collision free. It's too regular, it's collision free. And it's not hard to convince yourself that this thing is amenable. So the spectrum is actually, K is actually in the spectrum. Because if you take a big block and you apply the adjacency, you almost don't move. You stay with a very big overlap. So K is in the spectrum. So this actually can be even for amenable digraphs. But what we showed is that if A,
What are the distances between
the adjacency is the edges. So every vertex has two neighbors, which are, this guy has these two.
So go,
This goes down and then here.
yes,
It's
then
a-
go back there and it collides. So what,
It's a digraph.
yes,
a directed
yes,
graph.
Right. So go like this, then like this. Just start from the origin.
Mm-hmm.
Yes, go down 3 steps. You can also get there by going left, left, then right.
So I think it's the big
1, 2,
four,
3.
maybe?
Yeah. Okay, come on.
Okay. And,
Yes. It's like 1, 2, 4, 8.
basically, you change the k bit of
Yes.
the
So now it's like
It's something. It has a name, this graph? Okay.
I don't know.
But I know it. I was also happy that we found it because it makes things more interesting. Eventually, here is what we can do. If A is collision free, then the spectrum of A, what we call the 2 plus spectrum of A, is bounded by square root of K. So what is spectrum 2 plus of A? All the eigenvalues, now it's really eigenvalues, not spectrum in the larger sense. That there exists a F with a F equal lambda F, and F belongs to the intersection of L2 plus epsilon V for all epsilon bigger than 0. So you have to go a bit farther. This is the L2 spectrum. Maybe I didn't say that. Then this is, we always think about the L2 spectrum if I don't say anything else. And the point is, once you go to L2 plus epsilon, you're good. And how much time do I have? Okay, I don't have time. So I thought about actually showing you this because this is easy, relatively. You don't have much to play with. You only have this collision-free property. If you don't have a lot of, how do you say, netunim, assumptions, then the proof can't be too hard. That's the idea. We started with a representation theory of p-adic groups, and we had to work very hard for these results. But after we took all the theory, and everything we have is just the assumption of collision-free, the proof can't be very hard, and it's not. And then what we showed next is that furthermore, if X is a Ramanujan, let's say, so now X is a quotient of the building, so this is the d-dimensional building quotient by some group, and if this is a Ramanujan complex, then the non-trivial spectrum of any operator on X is contained in the 2 plus spectrum of this operator on B. So these are the two ingredients that eventually solve everything. For every collision free on the building, we have a spectrum bounded by the square root. And then for Ramanujan quotient, we show that the spectrum is contained in the 2 plus spectrum on the building. And this is how we get, so the corollary is again this cutoff diameter and so on.
How do you define the trivial spectrum for a general
That's like a page. Yeah, I'm skipping over this for a purpose. Eventually, you want it to be only the Perron-Frobenius eigenvalue, and it's well, all the eigenvalues of the same magnitude, which correspond to periodicity in your work. And it is this, but it was hard to show. That also took a lot of work to show that the trivial ones are also fine. Okay. So the fact that we have this very general theorem is what eventually surprised us. It was not hard to do it for GL, for Ramanujan complexes of GLD using all the existent theory, but because eventually we didn't use the existent theory, we showed it for something like all Boatitz building of semi-simple groups in general. Okay, so questions? Right, right. No, that's very important. So the corollary is that if T is collision free on B and X is a Ramanujan complex, then T on X, so it's like non-backtracking random walk on the tree is collision free. But what Parzanchevski showed is that non-backtracking random walk on the Ramanujan graph has this nice property. So this has cutoff and so on. Okay. Okay. So one thing is that at some point I said that, okay, there's something important here. So let's define a K regular digraph to be Ramanujan if the spectrum of its adjacency operator is contained in the union of the circle of radius k and the disk of radius square root of k. Because eventually this is also for random walk on the graph. This is what happened for the spectrum of the non-backtracking random walk. And this is what we get for every collision-free operator gives us a digraph with this property. So I said this is the main thing here. We have this digraph which are optimal expanders. And then Alex and Eyal said, yes, it's not interesting. The fact that you give something a name is not, does not make it interesting. One of them said that. I was a bit insulted. No. I thought it is interesting, so I worked quite a lot after that to understand these graphs. Now I wrote a survey about everything which I understood about this graph, and I'm trying to convince people that they are interesting. So if you look in the archive, I tried to convince people that these digraphs are interesting. Maybe you'll be convinced. And the other thing I want to talk about, and let me just say, we have now I have by not a lot of work of myself, but also by collecting relevant results from the literature, because people prove things, but they don't have a concept to relate it to. So there are analogs of the Alon-Bopana theorem, of LPS construction of Ramanujan graph, Alon's conjecture about random regular graph, so the directed version is also true by a very recent work, Kesten. So a lot of things we can do with graphs, with trees and Ramanujan graphs have directed analogs. Okay, and the last thing is, so going back to Lubetsky-Perez, they also showed that simple random walk on Ramanujan graph has cutoff. Cutoff is this phenomena that up to some point you don't see almost anything, and then after this point you see almost everything, which is, we kind of saw it. So it has a cutoff at time. So this is log k minus 1 n, because your simple random walk only expands by k minus 1 after the first step. And in addition, here you have k minus 2 over k, because k over k minus 2, because when you do this simple random walk, there is a chance of 1 over k every step that you go backwards. So this is like the expectancy of your progress, your drift. And they did that by relating simple random walk to the non-backtracking random walk. They already had the result for non-backtracking random walk, and then they described simple random walk as non-backtracking random walk with delay, with stuttering. And this is more interesting than non-backtracking random walk. And we wanted to do the same for Ramanujan complexes. All the walks that we proved these cutoff phenomena on Ramanujan complexes were directed walks, were not symmetric walks. We didn't have an analog for this, and we couldn't find an analog for this by the time we were working on this. But now this is a very recent work with Michael Chapman. We think we know how to do this in higher dimension. So let's write, for example, a theorem with star, because we still need to write it down and see that we're not cheating. For example, for B2. So let's do the two-dimensional case. A simple random walk on the skeleton has, let me just tell you that the degree is 2 twice p, so p squared plus p plus 1, where p is some prime. You remember that these complexes come from p-adic groups, so this is the p in the p-adic group we started with. So the degree is here, and the cutoff at Michael? log p בריבוע של n. So, Michael is already convinced, he still needs to convince me, that the game with cutoff is that you need to bound things from above and below. So, I'm still not convinced completely about this, but today maybe he will convince me after we talk. This is very recent work from the last 2 weeks or something like that. Let me just say the spectrum of the adjacency of simple random walk is contained in, so we have this k here, which is 2p plus p plus 1. So this is a trivial eigenvalue, and the non-trivial spectrum is contained in minus 3p, 6p. And the Ramanujan, if this was a Ramanujan graph, then this k would give me 2 square root of 2p squared plus p plus 1 minus 1, which is something like 2 square root of 2p, which is something like 2 2.8 p. So something like 2.8 p, and here we have 6 p. I'm just saying this is if you don't care about digraph and you don't care about complexes, it's a pity, but still what I'm claiming is that we have a graph, the skeleton of the building, which is not Ramanujan. The spectrum is kind of twice larger than what it has to be for Ramanujan, which makes perfectly sense because this is a skeleton of a triangle complex. There are a lot of triangles, so the graph has many, many, many loops of size 3. You cannot have Ramanujan, but you still have this optimal cutoff. That's the idea. Thank you.
Yeah, so concerning this collision-free property, so that's an entirely algebraic or geometric property, which means that you have an underlying tree structure. So what is this tree structure on the building?
So I showed one example, this geodesic work, that I work on edges without doing this, without going around. If I'm not going around the triangle, I'm not allowing this. I only continue from here to edges which don't share a triangle with this. That's one example of getting a tree structure. You will see a tree structure if you do this work on the building.
So you are saying that one can encode the boundary of the building with certain kind of geodesic?
Yes. Well, the boundary of this work, I mean, boundary probably has many meanings. So I'm saying if you look at the endpoints of this work with respect to different starting points, you will see a boundary of a tree.
No,
Yes.
for buildings, there is canonical notion of the boundary.
Yeah, this will not, but it will correspond to something like simple random walk, I think. I'm not an expert on boundary of buildings. I know this is exists.
It has nothing to do with random walk.
Okay, but there's something very subtle here. Also on a tree, if you take a non-backtracking random walk, you have this collision free. If you take simple random walk, you don't have it.
Yeah, precisely, because on a tree we have the geometric boundary and we encode this geometric boundary with geodesic.
Right,
So you say you can do the same on general building.
yes.
No, I want to understand the last statement that you said about the graph, where you have, it's not Ramanujan, but you have some optimal cutoff. So
It's not optimal because the degree is twice p square plus p plus 1, and the cutoff is at log p square. So I think this is I mean, that's why the asterisk here, we still need to convince ourselves, but I think in a sense optimal cutoff is remarkable, but in a sense non-optimal cutoff is kind of harder because the optimal also gives you one side for free.
one side for free.
Right. Yes.
So with these two theorems that you had, non-colliding, and do you really need a building, or is
No.
it something
No,
completely
not
general?
that was completely general.
So a contractible,
No.
official contract.
And any digraph, doesn't matter where you come from, which is collision free, the L2 plus spectrum is bounded by a square root. That's the other thing. The fact that for Ramanujan quotient, the non-trivial spectrum is contained in the 2 plus spectrum of the building, there you need the building.
Just one remark connected to this is one conjecture I've had over the years is that any expander sequence of graphs which are transitive and are an expander, so uniform expander, have cutoff.
I didn't know if this is still open. I hesitated whether to say it.
This is still open.
Mhm.
So we know it for the Ramanujan case, you have a transitive standard sequence, the uniform shows it. The lambda 2 is bounded away, take fix the degree d, lambda 2 is bounded away from d minus 1, and sorry, lambda 2 is bounded away from d, lambda 2 is bounded away from d, but we don't assume that it's Ramanujan. Question, does that imply cutoff? And then it's not optimal cutoff.
Sorry, no, I didn't want to.
So this, you don't know, if you drop transitivity, it's false.
I wanted to say that there also another student of Alex, Amitai Camber, which has related results. I don't know exactly in terms of cutoff, but it has related results for works on buildings. So if I got you interested on buildings and Ramanujan complexes, if I got you interested, then you should also look at his work, which is very rich.
Okay. Let's thank Ori again.
Thank you.